In this video, we'll be looking at the types of problems you'll see in the Ready, Set, Go section of Task 8.5. In the Ready section, you're being asked to evaluate different types of functions given an equation, a graph, or a table. The first example is an equation. We're given the function f of x equals negative 5x squared plus 7x minus 1, and we're asked to find the function of negative 2. So when x is equal to negative 2, what is f of x, or what is the output? We're going to substitute the negative 2 in for our values of x, or replace all of our x's with the negative 2, and we're going to simplify using order of operations. So first we are squaring that negative 2. Remember, if you're using a calculator, that you must put the negative 2 inside the parentheses before squaring it. And you can see that we get the 4 for negative 2 squared. And in the second term, we multiplied 7 times negative 2 and got the negative 14. We continue simplifying. The first term becomes negative 20 plus negative 14 minus 1, which equals negative 35. So when x is negative 2, the function of x, or the function of negative 2, is negative 35. Next, we'll look at evaluating the function when modeled with a graph. For a, b, and c, they're giving us the x values. So when x is negative 4, when x is negative 2, and when x is 0, they want us to find the y values. So when we go to negative 4 on our x-axis, we see that y is equal to 0. When x is 0, y is 0. And when x is negative 2, we go up and we see that y is 4. Finally, we are evaluating the functions when it's modeled using a table. So we're trying to find what is g of 1, or what is g of x when x is 1. When we look at our table initially, we notice that x equals 1 is not listed on our table, so it would be located in between 0 and 2, halfway in between 0 and 2. We can easily say to ourselves, well, what's halfway between 20 and 10? And we know that that would be 15. Mathematically, what we want to do is look for the rate of change. If they're not easy numbers, we need to know how to find that rate of change. This, again, is the slope. So we're using the slope formula, which is y2 minus y1 divided by x2 minus x1. So we can take any two of the y values. In this case, we're taking 10 minus 20. Placing that in our numerator, we get negative 10. And 2 minus 0. Placing that in our denominator, we get 2. What that means is every time we increase our x value by 2, we decrease our g of x value by 10. We don't want to know what the value is if we increase by 2. We need to know what it is if we increase by 1. So when we simplify the negative 10 halves, we get negative 5 over 1. That's our unit rate. What that means is every time we increase x by 1, we decrease g of x by 5. So decreasing 20 by 5 would give us 15. So what would g of 9 be? Again, that's not located in our table, but we can easily find that. If we've already found the unit rate, we've already found the rate of change, which is negative 10 over 2, or every time we increase x by 2, we decrease g of x by 10. So if we go from 6 to 8 for our x values, our g of x values would decrease by 10. Negative 10 minus 10 more would be negative 20. Now we can use that unit rate to increase x by 1 more and decrease g of x by 5 more. So we end up with 9. When x is 9, g of x is negative 25. Today in class, we worked on task 8.5, Giant Parthenon Wheel, where the idea of projectile motion was introduced. We looked at the effect of initial velocity on a projectile, as well as the effect of gravity. As we developed this understanding, we were able to build quadratic functions with a better understanding of what each term in the quadratic represents. We identified the first term as representing the acceleration due to gravity. The second term represents the velocity, the speed at which something travels, that's also the rate. And the third term is the initial height. In this set portion of your homework, you're identifying the key features in context. So if we look at this function, h of t equals negative 16t squared minus 96t plus 256, you can see it's modeled with both the equation and the graph, and this goes back to number 8, which is from what we did in class today. So Sam was on top of the giant Parthenon wheel, and he had an argument with his girlfriend, and she threw his sunglasses downward at a velocity of 96 feet per second. And you were asked to determine when they would hit the ground and some other questions. For the set portion of your homework, you're just going to be focusing on the key features in context. We know that the y-intercept, the 256, the third term in our quadratic, that represents our y-intercept, or our initial height. That's the height. That's how far he was above the ground when the sunglasses were thrown. Again, the time is 0. The x-intercept is 2, 0. That's when the sunglasses hit the ground. So at 2 seconds, they hit the ground, so the height was 0. And when we're looking at the domain in context, we're not looking at the entire domain of the quadratic. We're only looking at the practical domain. What's the domain that makes sense in the context of the story? So here, the domain is 0 to 2, including both 0 and 2, which is represented by the brackets. In this example, you can see that the red shaded portion of the graph, if time is our x-axis, is on our x-axis, it doesn't make sense, or it's not practical to look at the quadratic that's in the negative, that has negative x values, because we can't look at terms in terms of negative time. So we're only looking at the portion of the quadratic that's in quadrant 1. We can see that the initial height is 21, and that's when the time is 0. So our y-intercept is 0, 21. We can see that our x-intercept is 7, 0. So at 7 seconds, or whatever the unit of measurement is for the time, that's when the object hits the ground. The height is 0. Our maximum is at 25 feet, and it took 2 seconds for that to occur. So the vertex, or the maximum height, is at 225. We can see that it's increasing from 0 to 2 and decreasing from 2 to 7. Remember, when we're looking at our intervals of increasing and decreasing, we're using our x values. In the Go section, you're asked to solve one variable quadratic equations, which you can do either by using inverse operations with the properties of equality, or you can set the equation equal to 0, find the linear factors, and then using the zero product property, solve for the x values. We're going to do the latter in this example. So where you need to set this equation equal to 0, using inverse operations, we will subtract 9x from both sides of the equation, combine like terms, and we're left with 3x squared minus 19x minus 14 equals 0. Next, we're looking for our, our linear factors. We know that the first terms in each of our factors must have a product that's equal to the first term in our quadratic equation. So 3x times x gives us the 3x squared. We know that the last two terms in our factors must have a product that's equal to the last term in our quadratic, the negative 14. So we're looking for the factors of negative 14. If we look at the last set of factors, the negative 7 times 2, and we place the negative 7 in our second linear factor, when we multiply the last term in our last factor, the negative 7, by the first term in our first factor, the positive 3x, we get a product of negative 21x. When we place the positive 2 in the first factor, and we multiply that by the x, we get positive 2x. We know that the sum of those two products must equal the second term in our quadratic, or the negative 19x, which it does. Negative 21x plus 2x gives us negative 19x. If we look at that in an area model, we can see that the 3x squared minus 19x minus 14 is represented here. We have 3 x squares. Those are our gray squares that are x unit by x unit long and wide. So their value each is x squared. We have 3 of those. We know that the rectangles each have a dimension of x by 1. The rectangles in red represent negative x values. They have dimensions of x by negative 1. And we have 21 of those. The two green rectangles are positive x values. Those have dimensions of positive x by positive 1, and we have 2 of those. When we subtract when we add the negative 21 x's and the 2 positive x's, we end up with the negative 19 x's, which is the second term in our quadratic. The negative 14 is represented by the 14 small red squares. Those each have a dimension of positive 1 by negative 1, and again we have 14 of those. Now that we have our linear factors, we can set those equal to 0 using the zero product property. We can then use inverse operations to solve for x. In the first linear factor, we're going to subtract 2 from both sides and then divide both sides by 3. We're left with x equals negative 2/3. In the second linear factor, we're going to add 7 to both sides and we're left with x equals 7. The solutions to this quadratic are negative 2/3 and 7.